Hello everyone, this video covers lecture notes for week number 6. The main topic is modeling with functions. Modeling is just a fancy way of saying word problems. So pretty much all the problems in this section are word problems, but the good news is that these are problems you already know how to solve from the previous weeks. You just need to come up with the problem yourself first, and then you solve it. The objectives are going to be to create functions using geometry, such as area, perimeter, circumference, volume, etc. To translate given verbal cues into algebraic expressions. And then finally, to apply the techniques for finding the maximum and minimum, which we did in week 4 or week 5. Remember, you have a quadratic equation. The graph looks like this or like this, where this was a maximum and this is a minimum. So we already know how to do this, and now we're just gonna use it in applications. Let's try the first example. The problem says the following. So we're gonna modeling the volume of a box. So remember, we were going to talk about either volume, perimeter, area, and so forth. So the first question is asking you to model the volume of a box. Now, they had to give you specific conditions to get the box, and the conditions are the following. The width is 3 times its depth, and its height is 5 times its depth. Notice how everything is related to the depth of the box. Whenever you have a geometry problem or a volume or area, is always a very, very good idea to draw a diagram, always. So let's do that first, and you don't have to be a Picasso to do a box. Just to illustrate the point, so box could look like this. Okay, so here we have, this is the height, this is the width, this is the depth. Okay, this should be the height, not the length. Okay, now since everything is related to the depth of the box, let's call that one x. Then the width, it tells you it is 3 times the depth, so this will be 3x, and then the height, it would be 5x. Remember that the formula for the volume is equals to width times depth times height, or height times depth times width, it doesn't matter. So in this case, it will be 3x times x times 5x, which is equals to 15x cubed. So this is the volume of the box in terms of the depth, which we're calling x. So this is the answer to part B. So that's the volume in terms of the depth. Now the input is the same thing as domain, but this function is x, which is, remember, the depth, and the output is the volume. Now if we want to write the volume in terms of x, then b of x will be 15x cubed. So this is a formula for the volume, which depends on x, where x is the depth of the box. Okay. So part C is asking you find the volume of the box if the depth is 1.5 inches. So therefore this is asking you to find b of 1.5, which will be 15 times 1.5 cubed. Now you can pause the video and check with the calculator and this is 50.625. Here 1.5 is input because it's the value for x. In part D, they already give you the volume. It tells you that the volume is 90. Here what is given is the output, and they're asking you to find x, or the depth required to get 90. Remember, the formula for the volume was equals to 15x cubed. Since we already know that the volume is 90, so we have 90 equals to 15 times x cubed. If we divide by 15 in both sides, we have the x cubed is equals to 90 over 15, which is equals to 6. So therefore x is going to be the cube root of 6, which is around 1.8. So the depth of the box has to be at least 1.8 to have a volume of 90 inches cubed. All right, let's try the next example. So here, a gardener has 140 feet of fencing, and he wants to make a rectangular garden to put vegetables in. So rectangular, well, means this. So this is the length. This has to be the length. This is the width. And here the restrictions is the 140 is equals to 2L plus 2W, which is the perimeter. Now this is asking you to give an example of the dimensions of a garden that has this restriction, and to find the area. For example, we can do something like this. Let's say this is 60 feet. Therefore, this one has to be 60 feet. That's 120. So this has to be 10 feet, and this has to be 10 feet. Otherwise, it will not be a rectangle. And the area, remember, is base times height, so this will be 600 feet square. Another person could draw a different one. Somebody could do this. Say I want to put 50 here, so therefore that means this is 50, and this will be 20. This will be 20. Therefore the area will be 1,000 feet square. Notice, and this is very important for what we're going to do in the next page, notice that both of them use 140 feet of fence. But if you do this garden, you can only put 600 feet square, while if you do this one, you can put 1,000. So this one has a lot more area than this one. So the next natural question is, what should be the dimensions so that we get the maximum area? This is very important in business and economics because you want to maximize or minimize things. And the answer is going to be the vertex, which you learn how to find in week 4 or week 5. I forgot which of those two. Part B is a continuation from the previous page. Remember, this is what we have. We have a rectangle. We call this the length. This is the width. You can also call it x and y. It doesn't matter. And remember, we have that the perimeter is equals to 2L plus 2W. Now we can solve for any of them, but here is asking that the area should be a function of the length. So therefore the input is going to be the length, and the output is going to be the area. Now the area, as you can see, is length times width. And you want to change the width to L2, and you can use that from here. Remember that the perimeter is 140. So this is 2L plus 2W. Or you divide everything by 2, you have 70 equals to L plus W, or W is equals to 70 minus L. So therefore the area is going to be the length times the width, which is 70 minus L. And this is 70L minus L squared. Notice that this is a quadratic equation or a parabola that opens down. So therefore, indeed, it has a maximum value. And therefore, the area in terms of L is equals to 70L minus L squared. The next part is asking you to find the maximum area. Remember, the maximum is going to be the vertex. So all we have to do is find the vertex, which again you did this before. So this is what we have so far. The area, I'm gonna rewrite it like this. This is minus L plus 70L. And remember we need to complete the square. So I put the minus outside, and then this will be L squared minus 70L, because minus and minus will give you the plus. And remember, how do we complete the square? You're going to divide this by 2 and square and add it to both sides. So 70 divided by 2 is 35, and 35, actually minus 35. It doesn't matter, when you square is going to become positive. This is 1225. So therefore we're going to add 1225, and then we're going to add it here again. Remember that this is actually minus, so this plus that will give you 0. Remember that this becomes this part. This is minus L minus 35 squared plus 1225, and therefore the vertex are the coordinates 35 and 1225. Therefore the maximum area is 1225 feet square when the length is equal to 35. That will be the maximum area. Notice that if the length is 35, the width, which is 70 minus the length, so 70 minus 35 will also be 35. This is not by accident, so it's very important that you remember this result for your future classes, not just this class, but for calculus 1 and so forth. So therefore, if this is 35, well, obviously this is 35, this is 35, and this is 35. So notice that this is a square. So therefore, of all rectangles, the one that has the maximum area is always a square. And that result is true in two dimensions. In 3 dimensions, instead of area, you have volume. So therefore, the maximum volume will be given by a cube. Okay. Again, that's going to be very handy later when you take calculus, but also in this class. Right, now let's talk about a cube. This question is very, very important. Pay attention to this. This is the typical questions you have on the exams. They give you a shape or a figure or any geometrical surface, and they usually ask you to maximize or minimize something. So for example, let's say you have a cube, and remember, a cube means that all the sides are the same. Okay. So therefore, if this is x, this has to be x, and this has to be x. So the length, the width, and the height are the same. Remember, the volume has to be length times width times height, which in this case is x times x times x, which is just x cubed. Next, you need to find the surface area. Notice that a cube actually has 6 sides. 1, 2, 3, 4, and then the top and the bottom. Or you can say that it has 6 faces, and each face, so the area of the face is going to be equals to x times x, which is x squared. So therefore the surface area is equals to 6x squared. Here the question is asking you to find a function that models the surface area, which is this one, in terms of the volume, which will be this. So therefore you need to solve for x in here. So if this is the case, that means that x is equals to the cube root of v, or v is equals to the 1/3. It's the exact same thing. So therefore the surface area in terms of the volume is going to be 6x, but x is the cube root of the volume, then you square. So this is 6 times v to the 2/3, or you can write it 6 times the cube root of v, the whole thing square. It's exactly the same thing. This is a very typical question, not just in this class, but also in calculus 1, 2, and 3, and so forth, where you will have the two quantities, volume and surface area, related to a single figure. So if you want to have a specific volume, so if this is fixed, that means this number is fixed, then the question will be to minimize how much material you're going to use, which is the surface area. Or if this one is fixed, what will be the maximum volume that you can get from there. So you technically need two, but one of them is fixed and the other one will be variable. And the one that is fixed is usually called a constraint, and the other one is the one you're trying to solve, which usually is maximize or minimize. All right, let's look to the last problem. So here you have a can that holds oil, okay, and this one has a radius. Now the volume is equals to pi r square h, where h is the height of the can. This question is very similar to the previous one, except that instead of a cube, it has a can. Now the volume is 1000, so this is equals to pi r square h. This is what I mean by fixed. The volume is not going to change in this case. And it's asking you to write the surface area in terms of the radius. That means that the surface area has to have r as the main variable. Now the formula for the surface area is equals to 2 pi r square plus 2 pi r h. Notice that you already have the r in here, but you only want to have r. That's what it means in terms of r. So you need to get rid of the h. And to do that, you can solve for h here. So solve for h. So if we do that, h is going to be 1000 over pi r squared. So then if we plug it in here, the surface area is going to be 2 pi r squared, which is fine so far, plus 2 pi r, but now h will be 1000 over pi r squared. So all we do is just substitute h in here, which is this. So then if we simplify, this is still 2 pi r squared. The pi's will cancel, one of the r's will cancel, so this is 2000 over r. And now this will be the surface area that depends only on r, the pi is a constant, so therefore it only depends on r. And that's it.